we present CryoFormer, a novel method for continuous heterogeneous cryo-EM reconstruction. Our method can successfully reconstruct the heterogeneous structures of proteins and continuously model its conformational heterogeneity. It also enables highlighting flexible regions by analyzing its 3D attention maps. Given an input image, our orientation encoder and deformation encoder first extract orientation representations and deformation features. We use pre-computed pose estimations to pre-train the orientation encoder. We convert the orientation representation into a pose estimation, and transformed coordinates are fed into our implicit neural spatial feature volume to produce a spatial feature. The spatial feature and the deformation image feature interact in the deformation transformer decoder to output the density prediction. We can synthesize clean projections using Cryo-EM image formation equation. Our system is trained by minimizing L2 distance between the predicted image and the input image. To verify the effectiveness of refining the orientation encoder, we uniformly sample rotations from SO3 to produce synthetic data. We introduce noise to the ground truth poses to simulate imprecise pre-computation. Using these noised pre-computations, we pre-train our orientation encoder. During the main training phase of our model, we backpropagate the gradient of the image loss to fine-tune our orientation encoder till convergence. Orientation encoder refinement fixes inaccurate pose estimations and improves reconstruction resolution. We now show our results and compare them with baseline approaches. We start by performing heterogeneous reconstruction on CryoDragon's synthetic dataset. Our reconstructions match all the conformational states in the ground truth. We compare CryoFormer with CryoDragon and sparse Fourier backpropagation on our proposed PEDV spike dataset with SNR equals to 0.01. Now we move on to a more challenging setting with SNR equals to 0.001. Compared to baselines, our methods can better recover the details of the structure, even when encountering severe noise. By displaying multiple reconstructed states together, we can see CryoFormer disentangles different conformational states corresponding to the ground truth. Now we show the results of the reconstruction on real experimental datasets. We compare CryoFormer with CryoDragon, CryoSpark, and sparse Fourier backpropagation on ADS ribosome dataset. Our reconstructed volumes match or even surpass those from baseline methods, especially in certain details. We compared CryoFormer with CryoSpark, 3D Flex, and CryoDragon on precatalytic spliceosome dataset. Our result is compared with the results from CryoSpark and 3D Flex. As low-quality particles decrease CryoSpark performance, we remove them to improve the CryoSpark result. We then compared our result with the refined results from CryoSpark and 3D Flex. We compared our result with the result from CryoDragon, which is a recent neural method for Cryo-EM reconstruction. Among these comparison, our result shows outperformance in clearer secondary structure. For better reproducibility of our work, we will release the codes and the synthetic dataset. Thanks for watching.